Okay, welcome to today's lecture about earthquakes. So earthquakes are a pretty commonly known thing. You've heard about them. You've seen movies with plenty of them, I'm sure. And today we're going to focus on what an earthquake is, how you can identify where one has occurred, and the different types of seismic waves and seismic energy that get released when an earthquake happens. So a definition for an earthquake is listed here. An earthquake is caused by a sudden movement or trembling of the ground that's caused by a sudden release of energy when rocks along a fault move. Okay, so when we have one of the types of faults, remember, think about what they are: normal fault, reverse fault, strike slip fault. When you've got one of those faults happening, right? So I'll draw like a strike slip fault right here. We've got the two plates. No, they're not rectangular, but you get the idea. And one slides, let's say, north, and the other one slides just a little bit south. That releases a ton of energy, and that is what causes the event known as an earthquake. And I want you, if you can right now, maybe pause this and run and grab a rubber band. Okay, so pull that rubber band tight. Then you go ahead and do that, and then release it. Right. So this is called elastic rebound. This is a concept in physics, actually. So elastic rebound is a sudden return of elastically deformed rock to its undeformed shape. So other things have elasticity or elastic kinetic energy, elastic potential energy. But this happens in rocks when two plates are moving or when there's a crack in the rock. There's this release of energy where the rocks go back to that original shape, right? And that also releases energy too. So earthquakes occur when rocks under stress suddenly shift along that fault, right? So there's that sudden kind of, even if it's an inch or two, that slight movement along the fault. A review: a fault is a break in the body of rock along which one rock moves relative to the other, right? So whenever there's a break in the rock, remember, a fault is different than a fold. A fold, there's no break, but when we have a fault, we actually have kind of like a crack or a break in that rock, okay? So when one moves relative to the other, you've got a fault. So some other important words, we'll kind of call it the anatomy of an earthquake, right? So the different parts of an earthquake. The first one is the focus. So I'm going to draw like a kind of a, little bit of an earth right here. This is a small version of the earth. The first term is the focus. It's a location within the earth along the fault which the first motion of the earthquake occurs. It's almost like the first location, right? So if we're talking about a fault, okay, so let's see, the fault is located on the Earth's surface there, right? So, maybe there's a tectonic plate there, and another one there, right? So the fault would be like kind of right there. Focus is deep in the earth, okay? So it's down in the lithosphere, down in the deeper parts of the Earth's crust, located here, right? The epicenter, which is different, is the point on the Earth's surface above the earthquake starting point or focus. Okay, so epicenter is what you would kind of experience up here on the Earth's surface, where the focus is down here below the Earth's surface. So keeping those two terms straight is going to be important for you this chapter. Although the focus depths of earthquakes vary, 90% of continental earthquakes have a shallow focus. Okay, so meaning that they are not very deep, that they're kind of close right to the surface of the earth. So most earthquakes are not that strong, as you'll see in a minute, because they happen close to the Earth's surface. So earthquakes that have a deep foci usually occur in subduction zones, right? So when one plate is subducting underneath another plate, right? When one's kind of going down, that's where the deep ones usually take place, is when there's a fissure or crack down there, okay? Earthquakes that cause the most damage have a shallow foci, okay? So if the earthquake is happening kind of close here, that's where we feel it, okay? It may not necessarily release the most seismic energy, but it's doing damage to us up here on the surface when it takes place close to the Earth's surface. I'll show you here a good image of that. So here is a nice image of, here's the Earth's surface, mountains and whatnot. Remember, the focus is down below, down in the lithosphere there. And the epicenter is where we experience it here on the surface, right? So the epicenter located right there, okay? So the deeper the focus, the less damage we would experience up here on the surface. Okay, so if the focus, let's say, was moved up to here, it's kind of like being closer to a loud sound. Okay, so seismic waves move like sound waves. And the closer you are to a loudspeaker or a bullhorn or something like that, you kind of experience that sound energy more acutely, right? More a little stronger. The farther away you are from that bullhorn or that speaker, it's not as, you don't get that energy as, feel it as directly. Okay, so the same thing works here. If you're closer to the focus, like we are up here on the Earth's surface, like here I am here enjoying a nice hike in this valley here. If I'm closer to the focus, I'm going to feel that earthquake more strongly than I would if the focus was deeper in the Earth's crust. So a couple other terms you really need to know. These are the waves that are caused by an earthquake. So one kind of wave is called a body wave. It's a kind of a category. It's a seismic wave that travels through the body of a medium. Okay, so when we talk about a medium here, mediums or any substance that something travels through. Okay, so air is a medium, can be a medium. Water can be a medium, or rock can be a medium, right? Like lithosphere. Okay, so a body wave is a seismic wave that travels through a medium. So I'll just kind of draw that square to represent the medium. Okay, so the medium, again, like I said, can be anything, right? And waves travel differently through different mediums. We'll get to that in a minute. Another kind of wave is a surface wave. It's a seismic wave that travels along the surface of a medium. So this one has got a stronger effect near the surface of the medium than it does in the interior. So whereas a body wave travels through it, the surface wave travels along the surface of the medium, right? So here's another drawing of a medium, and in this case here, it travels along that surface. Okay, so the surface wave kind of obviously on the surface, body wave travels through. So as rocks along a fault slip into new positions, right? They kind of slip, they release that energy. It's almost like when you release that rubber band, it creates vibrations, right? And that's what all seismic waves are. Really, any wave, when you guys think about a wave and you get to physics, a wave is just a form of vibration. So seismic waves travel outward in every direction from the focus. Remember, going back to that picture you saw before, the focus kind of was that initial place where you feel seismic waves, and you kind of saw those drawings. It kind of looked like this, right? If you go back and look at it, there's actually arrows showing that that those waves travel in every direction from that focus. Now, this has some pretty big impacts. What this really means is that an earthquake located in Japan can be felt here, right? And that's why our seismic station down there, right next to room 52 in the basement, if you guys want to check it out or ask me, I'll take you over there anytime you want, that can receive seismic waves and seismic data from an earthquake anywhere, virtually anywhere on the planet. Because these seismic waves go in every direction, and they can travel right through solid objects like rock, magma, and whatnot. Okay, so some details about two kinds of body waves. We're going to focus on these quite a bit here and do a lab actually where we get to kind of chart these. We're going to call them P waves and S waves. So two types of body waves. So P stands for primary. Think about the word primary, right? It comes first, right? Primary schools before secondary school. So a primary wave, also known as a compression wave, is a seismic wave that causes particles of rock to move in a back and forth direction parallel to the direction of which the wave is moving. So I'll kind of draw it with my pen up here. So back and forth, back and forth, back and forth, kind of like almost like zigzagging back and forth, right? Parallel. So parallel means in this kind of that same direction. So the waves are going back and forth, like that kind of compression. So you see often a drawing of these will be like compression, kind of release, compression, release, compression, release, compression, release. You can really model this well, and we will in class with a slinky. And it's kind of a cool visual to see. You can kind of create these compression waves. P waves travel fastest, okay, and they can travel through almost anything, solids, liquids, gases, right? So primary waves are also called primary because they hit us. We receive that data first, okay, because they travel faster. And think about it like thunder and lightning. I'll get back to that in a second. But when you think about thunder and lightning, a thunderstorm, you see the lightning, right, before you hear the thunder. Okay, so the P wave is that initial signal that an earthquake is happening. It gets to us first. And the cool thing about P waves too is that the material or the medium that they're traveling through kind of changes how fast they can travel. So the more rigid or more hard, right? Think about a more dense rock versus a more light rock, allows a P wave to travel faster. Okay, so a P wave will travel faster through rock than it will water or air because rock is more dense than water and air. The next kind of wave is called the S wave or secondary wave, right? Because it's also known as a shear wave. It's a seismic wave that causes particles of rock to move in a side-to-side direction perpendicular to the direction of which the wave is traveling. Right? So side to side, so meaning it's going up and down, right? If the wave is traveling this direction, notice how it's moving perpendicular, right? Up and down relative to the direction of the wave. Whereas we look down at this picture below, you guys can kind of see how the lines kind of become a little bit closer together there. That's called a compression. Now when it releases, that's called a rarefaction. So we've got a rarefaction, compression, rarefaction, compression, rarefaction, compression. That's what the P wave looks like in a way. And again, here's the S wave with that up and down perpendicular motion. Now, S waves are the second fastest, and they can only travel through solids. So when they hit the water, when they hit air, they kind of stop. They cannot travel through just about anything. Okay, we're going to talk more about earthquakes and earthquake measurement and earthquake data and kind of interesting ways we collect that information, including information about our seismic center in another lecture. So I hope you enjoyed this one. I try to keep it short and sweet. Please ask questions. You will have a quiz on this in class the next day. So be ready for it and have a good day. Thanks for listening.